So today's topic, and I basically have to cover about 1.5 lecture in one lecture's time. So I'll skip over some of the details that we will actually work out in today's tutorial. So today's topic is quantum electrodynamics. Also known as QED. And we'll do only tree level. So just the tree level stuff. No renormalization stuff. So the Lagrangian for QED comprises of the Dirac Lagrangian for electrons and positrons, the electromagnetic Lagrangian, and an interaction Lagrangian. So you already know the Dirac Lagrangian. If you don't by this time, you're in trouble. You also should know what the electromagnetic Lagrangian is. We fiddled with it a little bit yesterday. The new part is the interaction between the two different kinds of particles. And that's given by the conserved current associated with the Dirac field coupled to the electromagnetic field. And minus E is a coupling constant. I think we attain E to be positive, but it doesn't matter. So remember that the Dirac Lagrangian has a global symmetry that if I take the fields and replace them by the fields multiplied by some constant phase factor, then that's a symmetry of our Lagrangian. Now, also, the electromagnetic Lagrangian had a gauge symmetry and that symmetry is A mu, if I replace A mu by A mu plus this thing. So this is not a global symmetry. It's because the parameters of transformation depend on space-time points. So that's we call it a gauge symmetry. But notice now, something strange has happened. The Lorentz invariant way of coupling, the minimum way of coupling, the electromagnetic field to the Dirac field has this form, right? There could be some non-minimal coupling as well, but nature doesn't seem to be interested in that. But this term is no longer gauge invariant. Yeah?
Do you call it minimal because it's the easiest way to couple?
That's what I call, but mathematicians have a different definition, apparently.
So why do we call it minimal?
Because you could imagine some other kind of coupling. For example, I don't know, like suppose you had something like this, right? That could also be a coupling, for example, right? But that wouldn't couple to the conserved current, right? We are trying to couple to the conserved current. This is a different object. So that, in my mind, that would be a non-minimal coupling. But I think mathematicians, there's apparently some very rigorous definition of what's called minimal. I've never seen it. So our QT Lagrangian is no longer gauge invariant. Doesn't seem to be gauge invariant. However, suppose we required our global symmetry to be replaced, the global transformations to be replaced by this. So now instead of this being just a constant phase factor, this now depends on space-time points. So I write the phase factor like this. And I had a plus sign here, and I have a minus sign here. I think there should probably be a plus sign. Let's keep a plus sign. And so now the phase factor is no longer a constant. So then what would happen to the kinetic term in the Dirac-Lagrangian? The mass term would still be invariant, but the kinetic term is like this. So that this term would now, like this derivative operator will act on this and bring down an IE, factor of IE. Okay, I chose a minus sign here, which you can do because this alpha and this alpha was not in principle the same, right? So let me use different symbols here and different symbols here. But now I'm choosing you'll see I have to choose the function in a very, this function has to be chosen to be the same function as this. So okay, so what we're doing is that we are taking a global symmetry and making it local, a global transformation. If we do that, then the kinetic term becomes part of the term, remains the same, but it picks out another term which comes from acting the derivative on this guy. So it brings down a minus IE, and there's an I here already, so we get a plus sign. So we get psi bar E, the derivative acting on the function A, alpha, this, okay? So if we were to do this, we get this extra term. Now see, if you make a gauge transformation like this term is not invariant, but what does this term become? L interaction becomes L interaction, and it picks up a minus E psi bar, this guy, contracted with the gamma matrix, psi, and then contracted so this is basically what you get. So now we see that these two terms actually cancel. So if we extend what we call by a gauge transformation to include not only this, but also this, then our Lagrangian theory is invariant. And we better do this because, as I said, that for the electromagnetism, a gauge transformation is nothing physical. It is just a different kind of redundancy it's a redundancy of description. Just as in GR, a coordinate transformation is nothing physical. Of course, it's very convenient to have it. So we can write, Schwarzschild metric in spherical polar coordinate and change to a new coordinate system when we go through the horizon, have, tortoise, Kruskal, coordinate system and things like that. But it's not something that is physical. Right, so we get our idea of gauge transformation has to be extended. So now what we mean by gauge transformation is some function alpha, and we can adjust so that the coupling E is over here. If we do that, then psi can just transform in this way. And now, importantly, this depends on space-time points. And then psi bar then transforms like so. So taking a global symmetry and making it local, and then seeing what other fields we have to change, what other things we have to change, is known as gauging a symmetry. So, okay, that was not very clearly explained. What I mean is that suppose we start with the Dirac Lagrangian and the electromagnetic Lagrangian. So there is no interaction term. These two kinds of particles are not talking to each other. They inhabit the same space, but they don't know of each other's existence. We notice that the Dirac Lagrangian has a global symmetry, and then we make it local. And we see, okay, the Dirac Lagrangian has lost it has generated a new term, right, under this new symmetry. And then we say, okay, what can we add to the total Lagrangian, so that this global symmetry is this new transformation is a symmetry of the Lagrangian, and it's precisely, if we precisely introduce this interaction term, we get a Lagrangian which is invariant. And so this process is non-gauging a symmetry. Usually gauging a symmetry introduces interactions. It's a trick by which you can find, some interacting theory. For example, Yang and Mills, they took exactly this path. If you read their paper, they took, say, two complex fields. So this is psi A. A is 1 and 2. So this is not a spinor index. And they wrote down like two it's like a Dirac Lagrangian for these guys. So they did something like this. And maybe they wrote down some mass. Yeah, they wrote down some mass as well. And then they said that, okay, if I think of this psi A as a doublet of Dirac fields, then this Lagrangian is invariant under a transformation where the G's are elements of SU2. But these are elements of SU2, which is they have to be, they're constant matrices. Otherwise, this Lagrangian will not be invariant under that SU2 rotation. And then what they did is they gauged the symmetry. And then asked what kind of vector bosons do they have to introduce so that the resulting transformations left the Lagrangian invariant. And they found the Yang-Mills, what we call Yang-Mills theory. So they took that path. So similar to the Dirac case, we can do exactly the same thing to our complex scalar field. So you can have a scalar QED. And so this is we have a complex scalar field part, we have an electromagnetic part, and we have an interaction part. And the interaction part, you can guess by analogy, will have a current that is associated with the global phase symmetry of this Lagrangian. And I think you did this in Dan's course, part of the course. That current for the complex Klein-Gordon field is this thing. And just as you couple that current to an electromagnetic field, you couple it here. And now if I say that my Klein-Gordon field now transforms, let's put this in this way, and the conjugate transforms like so, and this transforms in this way, then that leaves this whole Lagrangian invariant. There's a more elegant and deeply geometric way of re-expressing these statements, and that's by introducing a covariant derivative. And I will come to why we are calling it covariant. So if we define a new derivative acting on, say, the Dirac field by this, then under a gauge transformation, which by gauge transformation we now mean, this guys, then this Lagrangian, this derivative operator's action on psi is simply this. In other words, this object transforms covariantly under this transformation. Here, covariant is different from the GR covariant, but the spirit is the same. And similarly, if we define a covariant derivative for the scalar field, again we get under a gauge transformation so this is completely analogous to the fact that in GR this thing is called a covariant derivative, and under a coordinate transformation this thing becomes right, and you can figure out the indices. Okay, whereas a mu by itself doesn't transform covariantly; it transforms inhomogeneously. It's got this part, and that's similar to the fact that the Christoffel symbols also don't transform like this, but they have some inhomogeneous part, right? And sometimes, when we introduce interactions, so suppose we have some theory defined on flat space, and we say, okay, we want to see what this theory is like on curved space-time. What do? You make the prescription that wherever I have eta mu nu, I go and put g mu nu there, right? And you say that wherever I had partial derivatives, I put covariant derivatives, right? That's what Neil taught you, or should have taught you. And this is exactly what we're doing, is that if we go to the Dirac-Lagrangian, and we want to express this in terms of covariant derivative, we want to, if you go back to the QED Lagrangian, then if I now, you can see that Dirac plus the interaction part is now nothing but psi bar I covariant derivative slash minus m of psi. So the covariant derivative now contains in it automatically the interaction term. This is completely analogous to GR. Okay, what are the Feynman rules for QED? So now we have some extra Feynman rules in addition to what we learned before. And one of them is, for each Fermi vertex, you have a new vertex like this, where this is a fermion and this is a photon. A photon is not charged, but it has a space-time index. So associated with this guy, we now have E, IE, gamma mu. So the photon, electron, positron, or photon fermion coupling has now a gamma matrix. That is the most important change. And the photon propagator, so the photon propagator it's a gauge-dependent object. In the Lorentz gauge that we chose, it's given by this. So this is the momentum flowing in the direction. If you have an incoming photon, so a photon is coming in and hitting some, say, fermion, antifermion, some fermion line, then you have to add a polarization vector associated with that photon. And if the photon is going out, then you take the conjugate of that. And it may be that your photons are polarized in such a way that the polarization vectors are real. In that case, the complex conjugation is not important. So armed with these Feynman rules, let's write down the matrix elements for our first QED process. Incidentally, this is also the process that is given to you in your homework. So I'm giving you the answer to your part of the answer to your homework. Don't tell anyone, especially the instructors of this course. So electron, positron scattering. In today's tutorial, we will see an electron-positron annihilation. So what are the Feynman diagrams? Look at the vertex. We like time to go this way. You can choose it to go up if you would like. Then an electron is coming in. A positron is going out. An electron is going out. A positron is going out. How can we join these guys using that vertex and whatever propagator? It's clear that an electron has, this arrow must join up either with this line or this line, right? Otherwise, the direction of the arrow will have to flip. This arrow, for example, cannot join up with this line. That would violate charge conservation. So let's join this up first with this line. So this is possible. And then there has to be a photon coming out because that's the only vertex available to us. And then these guys can then only join up like this. So this is our first diagram. But we could have had another way of joining up, which was this guy could have joined up with this guy, and this guy could have joined up with this guy and give us this, right? Let me just redraw this little part so it's prettier. Okay. So let's label our diagram. So this is a PS, KR, P prime S, K prime R. So there is momentum conserved here. So the momentum going in this way is P plus K, which is, it's an S-channel diagram. And my convention is that I try to label the same particle. I would like to have the particles in the same position, external particles. So this is KR, K prime R, P prime S, K prime R, S prime, S prime, S prime, prime. And then this is P minus P prime. I think it's a T channel or the U channel, I always forget. Let's label mu and nu, the ends of the propagator, mu and nu. But in the final result, those labels won't matter, we'll see. All right, so let's write out the matrix elements. So what do we do when we see a diagram like this? What's the first thing we do? We pick up one of the Fermi lines to treat, fermion lines. And then we go against the arrow. Just can someone tell me what I should get for, say, this fermion line? I start against the arrow, so I start here. Is this an incoming electron or anti-electron?
Anti-electron.
Sorry?
Anti-electron.
Anti-electron. So what factor should I write down here? U or V? V. Should the V have a bar or not? Yes. Otherwise, we won't get a scalar. And then it should have this. And then we get here. What do we get? A vertex. What is our vertex factor? Minus IE gamma mu. And then what do we have here? Incoming electron or anti-electron? Oh, I couldn't hear you.
Electron.
Electron. Okay, so what do we put here? U or V?
U.
U. Okay. And then S and P. Okay, so and then we come to this guy. And this guy is minus I eta mu nu divided by P plus K. Why P plus K? Because that's the internal momentum, because we also have to conserve momentum at each vertex. So that's squared minus I plus I epsilon. And then we come to this guy. Where do we start, here or here? Here. Freddie used to start here, but he used to write from right to left. Freddie Cachaso? Yeah. So, okay, so we start at the top. So do we write U or V here?
U.
Huh?
U.
U, okay. Bar or not?
Yes.
Yes. Bars are, oh, otherwise it won't be a matrix element. Like a scalar, sorry. Okay. And then we have a propagator. Sorry, we already wrote the propagator. Then we have VR prime of K prime. Okay? Okay, and in the second diagram, we get a minus sign from Fermi statistics. And so let's take, say, this guy. Then we get a U bar and P prime, S prime. And then we have minus IE gamma mu. And then we have a propagator, mu nu. And then we have P minus P prime plus I epsilon, so X squared plus I epsilon. And here we have incoming positron, so V bar, R of K, minus IE gamma nu, U of R prime, K prime. So notice that the mu and nu index, they have been contracted over. So obviously our, that, you know, so yeah, that's basically how, whenever you have an internal line that gets summed over. So this is the scattering amplitude. Okay. Let's do another practice. Sorry? What am I missing? Oh, yeah, sure. Yeah. I always leave things unfinished. Right. Okay, so sorry? So,
Tibra,
yeah?
can you explain the last sentence again? I don't understand why we have U bar and V in this diagram.
In this diagram?
Yeah, shouldn't it be U bar, gamma, and U?
Which one? This one?
Yep.
This line or this line?
On the top line.
Yeah, you're right. Because, yeah, you're completely right. Sorry. That was a mistake, yeah. Because that's a, yeah. Thank you. That's called being on autopilot. Okay? Yeah, exactly. So thank you very much. It means you guys are learning. I'm amazed. Not because of you, the fact that I am teaching and you're actually learning. But I find that fact, maybe you just learn despite the fact I'm teaching you. Okay. Let's look at this guy. So mu is not part of our traditional QED, so we have to look at a different theory. It's an extension of QED, which now has an electron part. So that's why we have the electron wave function, field operator, and the mass of, so we have a Dirac Lagrangian with a covariant derivative for the electron, and we have another Dirac Lagrangian for the muon with the mass of the mu. So the mu here is not a space-time index. It's just labeling the fact that this fermionic field is a muon. And then we have the interaction part. And of course, very importantly, we also have the gauge-Fink part. Because otherwise, our propagator would not be well defined. So there are no direct couplings between the electron and the muon, but they talk to each other through a photon. So the electron-positron scattering is that an electron and a positron are coming in, and there would be analogous Feynman rules for the muon part. And then let's draw a double line for the muon. Okay. And let me label. I'm going to reuse this diagram. So let me label it a bit differently from what I've labeled in the first part of the lecture note. Notice that there is no vertex where the muon and the electron or its their antiparticles and the photons come together. There is no such thing. So the analog of this diagram is not there, because then it'll have to be an electron coming in, a muon going out, a positron coming in, and anti-muon going out, right? So this diagram, the analog of that guy is not there. If, for example, the photon was extremely massive particle, and we were so massive that, at the energy scale where we have this sort of things happening, we would not be able to create the photon, then, we could integrate out the photon, and then, we then would have an effective vertex like this. Anyway, that's just like kind of, this is not like our part of our course. So let me label this as P1, S1, P2, S2, P1 prime, R1, P2 prime, R2. Then the matrix element for this is, let's take this guy. So come here. This is a positron. So we have V bar, S2, P2, minus I E gamma mu, U of S1 of P1, and minus I eta mu nu, P1 plus P2 squared, because that's what's going through here, P1 plus P2. And then the next part is the muon part, and we don't need a different notation here. You can say, okay, let's just call this, put a mu here to make sure it's a different spinner. But if you're careful, we don't need that, because we already have the momentum and the spin label. So if we are careful, which I'm not always careful, this actually will be you'll be able to tell which spinners are the electron spinners and which spinners are the muon spinners. So okay. So as I mentioned before, in our scattering experiment, our initial beam is unpolarized usually, and our final our detectors they're not sensitive to spin. So what we do is that we, when working out the cross-section, we average over the initial spin and sum over the final spin. And this is a classical thing, right? This is a classical averaging process. So there's nothing quantum mechanical about that. So that's why to average and sum over the initial and the final spins, respectively, we actually first have to square this matrix. So we first have to square this matrix and then sum over and average over the spins. Multiplied by 1/4 because we are multiplying by a factor of half for each incoming beam. So in this case, factor of half because there will be spin up, spin down, factor of half for this guy because there's spin up and spin down. And this is like, that's why we get a 1/4. So because I've changed the labels, I can no longer use my notes. So let's see what comes out. 1/4. We have, so this is S1, S2, R1, R2. And we get factor of this, and then let's write the propagator for the photon, this part to be like this, and then we are going to use this to contract these guys, okay? So if I do that, then first let me write the whole thing. We have V bar, S2, P2. We have a factor of gamma mu, U, S1, P1. And then we have, so this is a scalar quantity. And then we have this guy, which is another scalar quantity, U bar R1, P1 prime, gamma mu, V of R of 2, P2 prime, this thing. And now we have to multiply it with the complex conjugate of this guy. Or let's just say this is the complex conjugate, and it's the same thing over here. Right. And there's complex conjugate here as well. Okay? So now look at the interesting thing is that this is just a number. So this is just A, some number. And if I take the complex conjugate of a number, that's the same thing as taking its Hermitian conjugate. So we can use this fact to reorder things inside our bracket. So for example, we can say V bar of S2 of P2 of gamma mu U of S1 P1 of star is the same thing as this thing with the dagger in it. And if you use that, then we can reverse the order, and then we have U of S1 P1 dagger, gamma mu dagger, and then gamma 0 V of S2 of P2, where gamma 0 came out of this guy. But remember that gamma 0, gamma mu dagger of gamma 0 is gamma mu, and that gamma 0 squares to 1. So that means I can insert 2 factors of gamma 0 here, and that means I can rewrite this as U bar of S1 P1 gamma mu of V of S2 P2. Okay? So taking the complex conjugate of this reverses the order and puts bar on U. You always have to check, because in this case we have a gamma mu matrix inside. It may have been something else. You have to check that what you're doing is, you cannot just blindly do the complex conjugation. So recall that this came from the electron and this came from the muon, and they are numbers, and we can rearrange them in this way. So we can now rewrite those guys in a way where the electrons are close to each other. So we can rewrite those. So we can rewrite so we have e to the power 4 by 4, and let's just bring this guy out. Then we have let's write the electron factor first, which is U bar of S1 P1 of gamma mu U of V of S2 P2, and as well as, there'll be something coming from here, which is basically this original thing. So we will have, say, V bar of S2 P2, and we have to be very careful about so this will have a different gamma matrix, a gamma nu. So let's call this gamma nu. And then we have U of S1 P1. Okay, good. And then times the second factor, U bar R1, P1 prime, gamma, say mu. Is that correct? Because I'm writing that factor first, and that factor contracts with this thing. So no, this should be mu. Yeah. Mu and V of R2, P2 prime. And then we will have V bar of R2, P2 prime, gamma mu, U of R1, P1 prime. Okay? Do you guys agree? So now note the spinor indices. So this, say, the spinor indices of the electron factors. So outside we have sum over S1 and S2. I'm just writing the spinor factors with the sum. So inside, let's write this guy first. Say we have V bar S2, P2, gamma nu, U of S1, P1. So this guy has some A, AB, and this is B. And what about this guy? This guy has some U bar S1, P1, C, gamma mu, CD, V bar S2, P2, D. Now, if we now use our favorite identities, which is VR summed over R of, say, P, V bar of R summed over P, it gives us P slash minus this, and U bar gives us P slash plus ME. If you use our favorite identities here, so we get this guy and this guy, see, they have the same spin label, they have the same momentum dependence, and similarly this guy and this guy. Then this thing becomes P2 slash minus ME. So now everything here is just matrix elements, right? I'm written everything in terms of matrix elements. So, and we are using the convention that repeated indices are summed over. So we can just change things around here, right? Everything commutes with everything else because we are keeping track of the matrix element. So I can bring this guy over here and then use this formula and write it like this, but I have to be careful about the matrix element. So so I have to say it is dA, right? dA. After dA, I have gamma mu A of B. And then I also look at these guys, and they're already in order. So I write P1 slash plus ME, and this should be BC, B of C. And then I have a gamma matrix. So we have a gamma matrix. This should have been a nu. You guys didn't tell me. And this is CD. So now if you look at the indices D, A, A, B, B, C, C, D, D. Therefore, I can write this as a trace. Okay? So this is how averaging over the initial states, spin states, and summing over the final spin states give us a trace over the spinor indices. So experimentally, the mass of the electron is about 100 MeV. Sorry, mass of the muon is about 100 MeV, what I was saying. The electron mass is half MeV. So if we can neglect the the mass of the electron, and then we can plug our, we can work out what the scattering cross-section will be, and the details are given in the notes, and this we are going to work out as analogous problem in today's tutorial, so I'm not going to do this now. I'm just going to give you the final result of the cross-section that you would get by putting this matrix element, calculating the matrix element for this cross-section, for this process. So the total cross-section turns out to be 4 pi alpha squared, where alpha is the fine structure constant. It's defined in terms in natural units. Well, it's defined in terms of the basic stuff. In this way, E is the electronic charge, and it turns out it's a pure number, and its value is 137.04. And this is the coupling constant for QED, so it's pretty small. So we can have some kind of faith in our perturbation theory. We're lucky. For QCD at low energies, that is not the case, and we cannot apply perturbation theory to QCD. You can draw these Feynman diagrams, but at low energies, they don't tell you anything about QCD. Turns out QCD is weakly coupled at high energies, so you can do stuff at high energies, but not at low energies. So in terms of this, the center of mass frame energy, and this is the energy of the individual particles, and this is the muon mass. So if you plot this guy against the center of mass energy, you get some curve like this. Sorry, it doesn't dip down, it just asymptotes.
The is always CM.
Sorry? E? No, this E is not the CM. This E is the energy of the particle in the center of energy of the individual particle. So it's half of CM. Now, when you work out the total cross-section, before you do that, you work out what the differential cross-section is. There's an energy dependence on the momentum phase space. The phase space that you integrate over, when you're calculating, there is like a momentum dependence, energy dependence there. But this guy also has energy dependency, P1, P2, and then we were using this in here, and there was P plus K. So suppose that this guy didn't have an energy dependence, it was just some constant number. Then the energy dependence of the total cross-section just come from the phase space factors. And then the prediction, so this is 2 mass of the muon. There is no, this process doesn't scatter below that energy. So the phase space result is something like this. So experimentally we see something, we see the prediction from QED. So this is for a generic theory, we would get something else. That's what it's saying, is that if the scattering was just some, if there was no photon exchange and things like that, then we would not get this. We would actually get something else. And comparing that to the phase-space result just sharpens that statement. So I want to quickly mention something. Perhaps, I don't think we'll have time to get there in the detail, but it's in the notes. What if so a lot of these diagrams, as you probably have noticed by now, they have a lot of different processes seem to have same kind of diagrams if you just rotate them by 90 degrees or something like this. They seem to have all these kind of symmetries. And there's actually the underlying mathematical amplitudes, they actually have a symmetry, and that's called crossing symmetry. And if you understand crossing symmetry, you can actually get the amplitudes for one process by using the amplitude for another process. So you can cheat. You can basically take shortcuts. So let me just tell you the statement of the crossing symmetry. Not good idea to erase this right now. I'll just erase the other one. So for example, if you consider the scattering of a muon and an electron, so if you had a muon and an electron scattering, so an electron coming in, going out, a muon coming in and going out, now, if you work out what the amplitude for this thing is, and then you do the averaging process, sum over it, and you get the final result, then you get, for your matrix element, so you get for your matrix element 1/4 this thing, something like this. The expression is Now the expression for this guy is also given in the notes in the lecture 14 part of it. And you can see that they almost look the same. You'd think that maybe with some relabeling of P1 and P2s, P1 primes and P2 primes, they can be made to look like each other. And indeed, they can be. And this comes from the fact that amplitudes have a symmetry called crossing symmetry. And if you're interested in knowing more detail, I can give you references. And the idea is this. If you have an amplitude with some particle, say in the initial state, that's equal to the amplitude of a process. So this means a particle in the initial state going to some other particle. And this is equivalent, mathematically equivalent to an amplitude in a process where that same particle is replaced by an antiparticle, but now in the final state with the momentum, for momentum reversed. It turns out, so there are different amplitudes. There are amplitudes for different processes. It turns out that to do one of these replacements, you don't really get from something physical to another thing that is physical. Usually you have to do two replacements. So you have to apply like the crossing symmetry for two incoming states. You have to switch two incoming and outgoing states, and then you get something physical. And the crossing symmetry actually holds at the level of amplitudes. Here we are actually at the level of the average and the square of the amplitude. So it should also hold there then. In our case, you can verify that if you take for this process the anti-electron, the positron, which had momentum P2, and then send it to the final state and replace it by an electron of momentum minus of P2. And similarly, the muon, anti-muon, sent to a final state of a muon. In other words, if you take the amplitude for that process and wherever you had P2, you put minus P2 and P2 prime to minus P2 prime, you can show that you basically get the amplitude for this guy, but I think you have to do some relabeling to get the. Yeah, right. So the way that I have chosen the labels for the momenta here are not consistent, are not exact. So once you do those replacement, you'll get an expression, but then you have to relabel those momentum to get this guy. Okay. So, but you basically get from one amplitude to another by doing those replacements. Sorry, I've been a bit sketchy on this one because I wanted to get to the last thing, which is an important trick that you should all know about. And the idea is that we have just learned a trick in which you can average over the initial spins and sum over the final spins, and then your amplitude, which had all these indices, they look very nice because you get this trace. And we did some trace identities in one of the tutorials, and you can use those trace identities and actually calculate them in great detail. And that's something we will do in today's tutorial. That's not a good interview question. We won't ask you to, at least I won't ask you to derive cross sections for stuff in the interview, but I will ask you to write down amplitudes. Okay. But you should know, because some of you are going to do particle physics calculations. Some of you will have to do cross-section calculations, so you should know. What if there was an external state, in the external state of a photon? A photon will have polarizations. And again, we probably, we want to look at experiment where the external polarization states are summed over. So there should be an analogous trick for photons, right? And it turns out there is some technical subtlety there. Which is resolved by gauge invariance. And that's like the last thing I want to mention. And it's called, and there's a typo in the notes as well, so I'm going to correct that. So our last topic is polarization sums. Polarization sums. So suppose you have some process which has an external photon, and it has some polarization, epsilon lambda. Lambda is the label of the polarization vector. So, yeah, something like this. And you have, for this process, some amplitude, m of lambda. And you can always write this as m times mu e of this lambda mu, the polarization part factored out. Now, when we try to do a sum or average over polarization, we should get something like this, because external polarization of photons can only be in two states, right? Because physically, a photon is polarized only in its two physical states. It could be left circular, right circular, or or something like that, or it could be perpendicular to each other. So you have to sum over the lambda. Now, if I use this, we get something like this. Now, the problem is that you'd like to use some kind of, say, completeness relationship where you're summing over lambda here and replacing it by something. But remember, the completeness relationship involved all four polarization, physical and unphysical. So we can't use this completeness relationship with impunity here. It turns out we can, and that's what I'm going to justify. So we use an identity or a which stems from gauge invariance called Ward identity to resolve this. Now, in the notes I given two arguments for word identity. The first argument uses some exercises that Peskin works out in chapter 4. So it's much more involved. I'm going to give the second argument, which I think is a bit easier. And the idea is this. So suppose you have some photon which is created from some outside source and which comes and interacts with other particles. Then the coupling of the photon that is created by this outside source to our electromagnetic current is given like this. So now A mu is some outside electromagnetic field. It can actually be even classical, where J mu is the fermion field. Then this thing has the form so this is the Peskin argument. I'm just briefly sketching it. Has this form where the final and the initial state are all these final all these external particles without the photon. And then Peskin argues that using the exercise from chapter 4, that this thing is 0. So the way to see it most clearly, in my opinion, is to start with the fact that, we had we have some polarization vector contracting with the amplitude. Now, if you do a gauge transformation, then polarization vectors in the Lorentz gauge, they change up to some constant times the 4 momentum of the photon. So if you do this transformation, then this combination does not remain invariant. You pick up some part where the momentum of the photon is contracted with the amplitude. So for this to be a gauge invariant result, it must be true that this thing vanishes. In other words, this has to be true. So it's a statement of gauge invariance at the level of the matrix elements, and that is what is called the word identity. So how do we use word identity? Let me use so we can use word identity to the polarization sums. Suppose our photon momentum was along like this. So the photon is propagating along the z direction. Then word identity tells us that the 0th component is equal to the third component. So then we can now take this polarization sum and apply this. So our polarization sum is m star lambda m of lambda, and that we can write as m star mu m of mu epsilon lambda star of mu epsilon lambda mu. Now what we can do is we can now use the fact that our polarization vectors satisfy this completeness relationship. So I forgot to write the 3 in here in my notes. So I'm just taking, yeah, and eta. So this is equal to eta mu nu. So this is our completeness condition. So to introduce it here, we see that because the zeroth component, we can add the zeroth component and we can subtract the square of the zeroth component and we can subtract the square of the third component. So if you do this, then we can write this as this sum now goes from 0 to 3. And I've introduced a minus sign because I want to now introduce a lambda lambda, eta lambda lambda. And remember that eta, the spatial components are -1, -1. So what this does is that it introduces, we are adding m0 star m0 and subtracting m3 star m3. But we know that that is 0 anyway because of this relationship. So we can add 0 and subtract 0. That's what we have done. And then we use this relationship to rewrite this thing as just the metric tensor. And this is the result. So the result is whenever you have a sum over the physical polarizations, you can replace that sum over the physical polarization by minus eta mu nu. This minus sign is missing from the notes. So, but to be able to do that, we had to use a statement about gauge invariance of the amplitude called Ward identity. So the last thing is I want to write down the Feynman diagram for Compton scattering. Oops. So Compton scattering. In the old days of quantum mechanics, Compton described how photons, after it was discovered that photons were that light was actually particles, Compton said, well, why not scatter light with other particles? And so like physical scattering, and so Compton worked out what would be the change of the wavelength of a photon if it scattered from an electron. So the electron-photon scattering diagrams are these. And there are two of them. So the electron can actually emit the final photon before it absorbs the initial photon. So let's write down the amplitudes for these guys. Let's start with this guy. So we come from here, we find an outgoing electron. There should be a prime here. And then an outgoing photon, polarization. And then there's also a vertex here. I didn't have to write the photon here because this is not a matrix. I could have just written it somewhere afterwards. So I get mu, and then I have an electron propagator, a fermion propagator, and this is like I p slash plus. Somehow the app I was using to write this ate the p's and q's. So and after this we come here, and let's write down those guys. So I didn't, there should be a nu here, and there should be a mu here, a mu here, and a mu here. So I should have a mu, and then the incoming photon has polarization E nu, E mu. And then we have an incoming electron, so we have a U S of P. This whole thing is one matrix, one long spinor matrix, except these, except for these polarization vectors. And then for the second guy, we have something similar. So we have U bar, S prime, P prime, epsilon nu, Q minus I epsilon. So we are just doing this. We have gotten to this point, and now we have to write the electron propagator. See that this I is outside. See that the momentum in this case is P minus Q prime. So this changes P minus Q prime slashed P minus Q prime whole squared minus M squared. The outgoing, and then we reach this point and we see an outgoing photon. So we have put a star there, and then we put the corresponding vertex factor, and then we get our incoming And this is our final result. And for compound scattering. If you wanted to work out what the total cross-section of this is a very long, it's a bit of detailed calculation, and you'll have to use this result there. And lots of textbooks, including Peskin, does it in a lot of detail. Schwartz also does it. It's a very famous calculation, and I highly recommend that you do it, but I think I'm going to stop there. Thank you. Questions? Yeah.
You were saying earlier that you can't have an interaction between a muon and an electron, like
right.
you're only talking to the photon.
Yeah.
Why is this?
That's just how it is.
Because we have muon decays where we just have W boson. So why is the photon?
That's how it seems. No, yeah. Sorry, yeah. At the energies we are looking at, the weak interaction effects are not important. I mean, of course, in higher, they are leptons as well, right? So we are not considering their weak interaction. We are only considering the electromagnetic interactions. Okay? So, I mean, there are others. So the covariant derivative in the standard model it has other terms in it. It's not just it has an electromagnetic. Like if you look at the covariant derivative, it'll have an electromagnetic part, right? And then it'll have a gluon part. I don't know. You want to call it a gluon part, and then you will have a part which is, say, a weak interaction. So these are the SU2 generators, and these are the SU3 generators, and this is the U1 generator, right? So all of the fermions will be acted on this, right? So they will all interact with not just photon, but also gluons and also vector boson. So yeah, there will be those interactions, but they're very heavy and they're very short-ranged. And sorry. For the muon and the electron, this won't be there because they don't couple to. It's the hadrons that will have that part. So, there's a whole big sort of complicated list of what the charge is and the group theory numbers of each states are, and that'll be treated in more rigorous way. Well, that'll be treated in the standard model course. Okay? Any other question? Well, in that case, I'll see you guys at 3:45 today. Thank you.